friends, in the last two lectures we understood how to derive the stiffness matrix for a beam element without considering the axial deformation, and we also said very clearly out of the 16 coefficients of the beam matrix, stiffness matrix, if we are able to derive only the 4 coefficients, remaining 12 can be easily derived based upon these 4 coefficients. We have learned from the first principles how to derive these coefficients for a beam element. We made an important assumption in that derivation, saying that the beam element has uniform flexural rigidity, which is uniform EI. Now, let us take an example. If I have a beam without uniform EI, that is varying EI, how do we derive a stiffness matrix? So, let us take an example of a beam which is shown in the screen now, which has got a depth which is varying from 600 at one end, 600 mm, okay, to 400 mm at the other end, for a length of 5 meters, and let the cross section be 300 mm wide. Okay. This is 300 mm wide. The beam is like this. So, now the beam has got varying depth. So, the EI of the beam will now vary even though E may be constant, same material, but moment of inertia will vary, okay, continuously from this point till this point, okay, or from this section till this section. How to handle this problem? So, the question is derive the stiffness matrix for the beam element with varying EI. Okay. We also say neglect axial deformation. Let us do this problem now. So, let us say I divide this beam into 10 parts. Say this is 600 here and this is 400 here. So, what I do? I divide this into 10 parts . Okay. So, this is 600 and this is 400, 10 parts. So, now I mark these 10 parts with different moment of inertia. We already know that the section has width of 300, okay, width of 300. Therefore, the moment of inertia I will be actually equal to 300 into 400 cube by 12, which actually is equal to 1.6 10 power 9 mm to the power 4. Okay. Now, I want to calculate the moment of inertia at different steps as indicated. Let us mark these steps as, let us say I1, I2, I3, I4, I5, I6, I7, I8, I9 and I10, where I stands for the moment of inertia and 1 to 10 stands for the number of strips. So, I can keep on estimating this value. For example, I 1, okay. I want to find I 1. I would like to know the depth here. So, if this is 600, let us say this depth will be 580. I will write down the value, this is 580. Okay. This depth will be 560, because there is a gap of 10 and this total is 5000, okay. It is 5 meters, you can see here this is 5 meters. So, each is 50. So, keep on dividing this. So, I get 560, similarly 540, 520, 500 this depth, okay. And this will be 480 and this will be 460 and this will be 440 and this will be 420 and of course, this is 400. We also know that the average thickness here is 600 and 580. So, this will be 590, okay. This is 590. Similarly, I can find average thickness at the middle of every section. So, I would say that if this value is h, this will be 1.5 h. Okay. Therefore, I can convert these values into ratio of this h. For example, this will be 1.475 h. So, let me draw another figure saying that for I 1 what would be the h, okay. This is strip value and what would be the h. So, I 2, I 3, I 4, I 5, 6, 7, 8, 9 and 10. B is same in all the cases, only h is going to vary. So, I am now working out the h for the average thickness. So, for I 10 it is going to be 1.475 h, okay, and I 9 1.425 h and I 8 1.375 h, 1.325 h, 1.275 h, 1.225 h, 1.175 h, 1.125 h, 1.075 h and 1.025 h. Please understand these values are related to, let us say this value is related to 590 m. So, it is nothing but the average value of the 10th strip. Okay. Similarly, all these are average values. Once I have this and B is same, I know very well that this I 1 can be expressed in terms of I, which will be 1.025 q of I, which is 1.077 I. Similarly, this will be 1.075 q of that of I, which will be 1.242 I. Similarly, this will be 1.424 I, 1.622 I, 1.838 I, 2.073 I, 2.326 I, 2.60 I, 2.894 I and 3.209 I. So, all moment of inertia at different sections expressed in terms of I, as you see in this table, and these values are easily computed based on the average thickness of each strip. Okay. Once I do this, the next step is to compute the loading diagram. So, let us say I have a beam which is simply supported. I want to apply a unit moment to the beam. So, I am deriving the flexibility coefficient unit moment to the beam. When you do that, the beam will deflect like this. Let us say this is going to be my delta Jj and this is going to be my this of the ith beam, this is going to be my delta Kj of the ith beam. Please recollect, this is my jth end, this is my kth end. I have given unit moment at the jth end, I get delta Jj and delta Kj for the ith beam. So, this is my ith beam. Okay. Now, this unit moment can be also distributed between these 10 strips. I apply unit moment here, okay, this is unity, and I give 0 moment here. There are 10 strips. Okay. So, let us try to find out what would be the value of these strips and the corresponding moment caused by this. Okay. Let us do this. So, for example, at this center this is going to be 0.95, at this center this is going to be 0.85, at this center it is going to be 0.75, at this center 0.65, at this center 0.55, at this center 0.45, at this center 0.35, at this center 0.25 and at this center 0.15 and at this center 0.05. Okay, these are the moments we have. Now, I have the I diagram here, I have the I values here, I have the M values here. Okay. Now, I want to create the M by E I diagram for the conjugate beam. So, this is my beam which will have the loading diagram according to the strips. Let us mark the strips. There are 10 strips 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let us draw the M by EI diagram. M is known, E is known and I is known. Okay. For example, this value will be, let us say, for the 10th strip, for the strip number, let us say M by EI ordinate. Okay. Let us work out this. Let us try to work out for the 10th, for the 10th strip, 9th, 8th, 7th, 6th, 5th, 4th, 3rd, 2nd and 1st. So, now this is unity, this is 0.9. So, the average is 0.95. So, the ordinate here will be 0.296 by EI, because M is 0.95 and I 10 is 3.209. Okay. So, if you apply these two, you get 0.296 by EI and this will be 0.294 by EI and this will be 0.288 by EI, this will be 0.279 by EI, 0.265 by EI, 0.245 by EI, 0.216 by EI, 0.176 by EI, 0.121 by EI and 0.046 by EI. Okay. So, let us try to mark this here 0.296, 0.294, 0.288, 0.279, 0.265, 0.245, 0.216, 0.176, 0.121, 0.046. Okay. So, let us say this is my M by EI diagram, which now become the loading diagram for my conjugate beam. So, this is my M by EI diagram, which is actually the loading diagram. Okay. So, correspondingly, for example, this value will be equal to 0.296 by EI and this value will be equal to 0.046 by EI and so on. So, if you want to really do the calculation, 0.046 EI can be explained as 0.05, that is the moment, divided by the I value is actually equal to 1.077, is it not? So, 1.077 will actually give you 0.046 by EI. Similarly, all of these things can be calculated. Okay. So, this becomes a loading diagram. Therefore, let us apply the loads. On this beam and try to find the reactions. Okay. So, what I do, I call this end as let us say A, this as B. To get VB, I should take moment about this point. Okay. Now, to get VB, that is reaction at the Bth end. So, taking moment about A, we get, let us see what do we get. I will get Vb, which will be actually equal to this span is 5 meters, each one is 0.5, okay, because the total is 5 meter 10 strips. So, each one is 0.5, is it not? So, I should say V B will be equal to 1 by 5 of 0.5 by E I, which is the strip width. Let us start taking from 1 by 1. The 10th strip is 0.296, okay, and the lever arm of this will be 0.25. So, I should say 0.296 into 0.25, okay, plus the other one is 0.294. So, 0.294 into the lever arm of that will be 0.5 plus 0.25, which is 0.75. It means this will be differing by 0.5. Okay. So, plus the next one is 0.288 into 1.25, okay, plus 0.279 into 1.75, because they differ by 0.5, plus 0.265 into 2.25 plus 0.245 into 2.75 plus 0.216 into 3.25 plus 0.176 into 3.75 plus 0.121 into 4.25 plus 0.046 into 4.75, which will give me V B. If you work out, V B will be 0.451 by E I, but with the downward sign, because you see here these will create an anticlockwise moment about A. So, V B will be reversed. Okay. So, V B is obtained now. Now, I can find easily V A. So, V A will be actually equal to 1 by E I of the total force, that is 0.296 plus 0.294 plus 0.288 plus 0.279 plus 0.265. I am taking only these values, okay, plus 0.245 plus 0.216 plus 0.176 plus 0.121 plus 046, 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values into 0.5, because 0.5 is the width of the strip, width of the strip is 0.5 into 0.5, that is the total force. I subtract 0.451 from this to get V A, which will be 0.662 by E I, which is upward